Okay, guys, welcome back. And before we get started with the actual course material, let's actually discuss or recap what we have done so far in the class, just to keep things in perspective, right? Now, again, this course is all about designing digital systems, designing circuits that can perform computational capabilities, right? Uh, so, towards that, we discussed, we started out by discussing basic building blocks, the basic building blocks that would enable us to design these systems by putting these building blocks together in the correct way, in the most efficient manner possible. We are designing these systems that are cost efficient, that can perform what functionality we desire them to be performing, okay, and we can design these systems using cost effective, power efficient manner. Okay, again, that basically entails designing the most simplified versions of the functions. Again, it's not a unique function that can unique design that can conform to that problem statement or the design specification, right? uh, so we are looking at obtaining the most simplified function that can actually achieve that can actually allow us to do that. Okay, and towards that, again, we formulated some rules, Boolean algebra, that we can actually utilize to come up with these simplified functions. So that was one of the approach of simplifying functions. The other approach was, of course, the K-map approach, which we discussed over the last few classes. Okay, so both of these approaches can allow us to design these functions in the most simplified fashion. Okay, and in the last few classes, we are basically trying to look at applying those concepts, right? The concepts that we have learned, especially the K-map approach that we have learned in trying to design these functional systems, right? And towards that, we have looked at the example of an XS3 code converter. This is basically a circuit that can allow us to uh, perform the nines complement operations simply by uh, inverting the, the individual bits, right? Just like how you get the ones complement of a given binary number by inverting each individual bit, that gives you the ones complement. Now, can I design a system by which, or a code by which I can be able to perform nines complement operations on BCD numbers, binary coded decimal values, uh, as simply as finding ones complement of a binary number, like as simply as inverting the individual bits of these binary coded decimal numbers. Okay, of course, the binary coded decimal numbers have to be converted into the XS3 codes, and then you can actually, when I invert the individual bits of the XS3 codes, then I get the nines complement of the corresponding number. Okay, and we have looked at the way that these systems have to be designed. Uh, First, we should understand what the inputs are to the system, what the outputs are to the system, and what that system has to do, how the outputs are dependent on the inputs, what should we be doing on the inputs to get the outputs, right? So if we formulate the rules in the XS3 code converter, all we are doing is basically adding 3 to every binary coded decimal value that is applied as inputs. We are adding plus 3 to that input, and that gives me the corresponding XS3 code. Okay. Now, once I know that information, I'll put that information down in the form of a truth table, right? And I would find out the output functions for each output independently as a function of the given inputs, because each of my function is a function of the given inputs, right? So I would find out, I will have individual K-maps for each function. For functions that are simple to see from the K-map itself, we can actually directly write down the logical expression for the function. And that's how we basically obtained the realization of an XS3 code converter in the last class. Now, the other example that we have taken, again, and this is very relevant, because ultimately, you know, we want to be in our own world, right? We don't want to be working with binary number that we are not used to working with, right? And it's a very tedious operation as well. We are more used to working with decimal operations, decimal numbers. We are more used to seeing pictures, not zeros and ones on screens, right? So when I'm trying to enter information, because ultimately what I'm trying to do with my computing device, whatever device I'm building, is to make my life easier, right? To make my computations easier, right? So whatever I'm designing, uh, I need to ensure that at the end of the day, my operations are simple. The interfaces are intuitive, right? Something that I'm more used to. Uh, so when I'm entering information, that the format of entering information should be in a format that I'm familiar with, I'm comfortable with. Like for example, when you're doing operations, you do your operations in decimal numbers. So when I'm trying to compute some certain operation in decimal, I would be entering numbers as decimal digits, right? And whatever happens inside the device, I don't really, as a lay person, he's not really concerned exactly what's happening. In fact, as a matter of fact, even before you come to this class, I don't know how many of you actually wondered what's happening at the device level, inside the device itself, right? And if you actually uh, took the pains to actually know what's happening, right? Although it's very interesting to know exactly what's happening, but most of the people, don't care. As long as the device works, as long as your smartphone works, you don't really have to care exactly what's happening inside the device. Of course, as engineers, we have to do that. We have to care about what's happening because we want to design better systems. We have to improve upon what we already have, right? That's how leads to technological innovations. All right. So you need to always have an interface between the user and the actual device, right? The interface could be an input device or a peripheral that allows you to input information to the device. That interface could also be another peripheral that allows you to display information in the format that you're more familiar with. So you need to always, and of course the device itself can only identify can only work with zeros and ones, the voltages or different voltage levels, right? Uh, so so we need to have some kind of a decoders and encoders that form as interfaces between your peripherals. When I say peripheral, that could be a display device, that could be a keyboard, that could be a peripheral that is attached to your device. Okay, and what the peripheral does is it takes in information or it displays information in the known formats. But on the other hand, it interfaces with a decoder that would decode what you have inputted into a binary format or decode the binary format to a display that you're familiar with. Like for example, in the last class, we talked about how to implement a 7-segment display decoder that would allow you to display binary coded decimal values as decimal digits, right? Each decimal digit is encoded within the device as a binary coded decimal value. And when we want to see it, I would like to see it as, again, back as a digit, like a decimal digit. And this 7-segment display decoder allows you to do that. So that's exactly what we have covered in the last class. Okay. Again, as an example of the application of K-maps, we have actually designed these systems. I hope you had a chance to look at and complete the design process for the 7-segment display decoder. I know we have done it for one of the uh, uh, outputs of that 7-segment display decoder. Okay. All right. And towards the end of last class, we also discussed this parity encoder. Okay. Again, as another example of how you can apply K-maps in your design, the parity encoder. Again, this will be more relevant towards communication systems, digital communication systems, where you're trying to send information through a channel that could be a noisy channel, right? And this noise can act on your data that you're transmitting, and that can, because again, your data is in terms of, especially in today's world, this data is all in terms of uh, digital information, right? Zeros and ones, right? Or in other words, levels, 0 level and 1 level, voltage levels, okay? And these voltage levels can be getting corrupted by the noise, right? You have so much of electromagnetic interference in the channels that can basically corrupt these levels. So your 0 level can become a 1, one level can become a 0, and what you're receiving is not exactly what you're transmitting. So there is some noise that is introduced into your system, and we need to find a way to somehow detect that errors and also correct for that errors. And there again, there's a whole, you can do an entire course on digital communication systems, an entire graduate course on digital communication systems, where you learn about the different codes, different methods available for error detection and error correction. Okay? One of the very simple way to understand that, one of the very simple way that can be done for at least to detect is the parity encoder that we have discussed in the last class, where what you're trying to do here is you have the transmitter and the receiver, and the transmitter is basically sending these data as data packets. So we are sending it as, let's say, 4-bit data as a data packet, or 8-bit data, depending on what kind of data you're working with. And so basically you have the data, and for each data, before you send it, you add what is called a parity bit. So if you're working with odd parity, for example, and this is what we've discussed in the last class. So you have a parity bit that is added to your data before you actually send it through the communication channel. Okay, and so let's say your data is for odd parity. Of course, if the number of ones in your data stream, number of ones in data is odd, so this is how you formulate the rules for the odd parity generation. Is odd implies your output for the parity generator is 1. If the number of ones in the data stream or data packet is even, that means your output is 0 at the end as an output for the parity encoder. Okay, so what that means is, if my data in this case, let's say I'm trying to send a data, in this case I'm trying to send 1011 through my communication channel, a 4-bit data, and I see that the number of ones are 3, so that's an odd number of ones. So I would add a 1 on my parity bit location, and I will send this entire data as a single data packet over the communication channel to the receiver. The receiver receives it. It counts the number of ones in the data, the data portion of the packet received, and compares that to what you have sent. And then if there is a mismatch, then that tells the receiver that you have some error, some noise or some error that occurred during the transmission process. And then you need to apply some error correction or ask the receiver to resend that data packet. So that's how it works. Okay. So now let's design this. All right. So let's design a parity encoder for a 4-bit data packet. That means I'm designing a system. Again, I start with the basics. Right. I start with the level 0 diagram. So I'm trying to design an odd parity generator. Parity bit generator that takes in the data packet or the data that you want to send before you actually send it on the communication channel. Okay. So let's say we are working with 4-bit information, 4-bit. That means I have 4 bits of input applied to my data to odd parity generator. Okay, let me call that P0, P1, B2, B3, and I get P, that's my output P. P odd, let me call it P odd, P0, PO. Okay, so every time I count the number of ones, and every time I have odd number of ones, my P0 is a 1. That's how I define the my output. That's how my output depends on my inputs. So I've drawn my level 0 diagram showing exactly how many inputs are applied to my system, exactly how many outputs are going out of the system. In this case, I only have a 1 output, and I know the relationship between P0, my output. Again, let me just, I don't know why I did that. P0, my output, and my inputs. Now is the time to put together that information in the form of a truth table, and let's see what we get. So that's my level 0. So as you can notice, I'm always approaching my problem in a specified format, in a specified sequence of steps. And I would advise you to do the same thing when you're asked to design a system, you approach this in that specified sequence of steps. Okay, so that way everything is organized. You're approaching the design process in a more organized fashion. Okay, all right. So again, I have what do I have? I have 4 inputs. Okay, that's my output. Let me list out all possible combinations. I have 16 of them. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. I have my 16 combinations. And how does my output depend on the input? In this case, I just count the number of zeros. So 0, all zeros, that means I don't have any ones. I consider 0 as an even number. So I will just put a 0 there. For 0, 0, 0, 1, I have single 1, that's an odd number of ones, that's a 1. Odd, even, that's a 0. Odd, that's a 1. Even, 0. Even, 0. Odd number of ones, that's 1. Odd, even, odd, even, odd, odd, even. So all I've done is count the number of ones in my input, 4-bit input, and just apply P0 as a 1 for if I have even number of, if I have odd number of ones, 0 if I have even number of ones. Now I have to basically put that information down in the K-map, and let's see what we get. And it's a regular process, right? We have, once you have the K-map, it's just a matter of finding the function and obtaining the function in the simplest form. So good thing I only have one function to work with, so that's one good thing. So let's actually do it. So that's my K-map, a 16 cell K-map. I have B3, B2, B1, B0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay, let's put down those ones. Okay, so I have 0, 1, 1, 0. I have 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1. Then I have 1, 0, 0, 1, 1, 0, 0, 1. And then I have 0, 1, 1, 0, 0, 1, 1, 0. Okay. So this is the K-map I would obtain for this odd parity bit, odd parity generator, P0. And now let's try to see, let's try to combine those ones and see what we get. How do we combine them? You see any ways of combining these adjacent ones? Do you see any adjacent ones here? I don't see any. Right. There are no adjacent ones. That's the worst possible K-map you can imagine, right? So each of this cell is a combination itself. So the only way I can do this is to combine each of the cells. So each of my prime implicant in this case is a single combination. That's my prime implicant. That's another prime implicant. Another one, another one, another one. So what is my expression then? My P0, I can write this as B3 prime, B2 prime, B1 prime, B0, plus, again, B3 prime, B2 prime, that will be B1, B0 prime, okay, plus B3 prime, B2, B0 prime, but which one? Here? Yeah, that's correct. B1 prime, B0, B1, B0 prime, that's correct. Thank you. Plus B3 prime, B2, B1 prime, B0 prime, plus B3 prime, B2, B1, B0, okay, plus here I have B3, B2, B1 prime, B0, plus B1, B3, B2, B1, B0 prime, plus B3, B2 prime, or this one, B1 prime, B0 prime, and B3, B2 prime, B1, B0. And that's the simplest expression I can get with the fundamental gates. Can't do any further simplification. At least with the K-map approach, can't be able to get anything further. That's the simplest sum of products expression, which is also, in this particular example, the simplified function is also the canonical sum of products expression, or the canonical expression, which is interesting. Okay. All right. But can I do something else? Can I see if I can do anything else? All right. Now you'll notice that I cannot combine and eliminate terms here, like I could have done in for other functions. Here I cannot combine terms and eliminate some variables here. But what I can do is I can express P0 as you can see here. If I notice this expression and this expression, I see that B3 prime, B2 prime are is a common factor. So I can take that as a common factor, and I can express this as B1 prime, B0 plus B1, B0 prime. Likewise, here I can take B3 prime, B2 as a common factor, and do the same for the rest of these combinations and see what I get. Okay. In other words, for this particular case, I would take B3 prime, B2 prime, which is a common factor in both of these terms, as a common factor. I would write this in this way. Okay. So that will become B3 prime, B2 prime, comes out, and then I have B1 prime, B0, and B1, B0 prime. And then of course I still have these expressions. I'll do exactly the same thing for the rest of them as well. So in this case I can see that B3 prime, B2 is a common factor. So I can take that as a common factor, get rid of this. So let me actually put it down here. So that becomes B1, B0. Likewise, do the same thing here. I see that B3, B2 is a common factor. I can take that out of the expression and write this as B1, B0 prime. Same thing here. I'll take B3, B2, B3, B2 prime as a common factor, in which case I'm left behind with B1, B0. So far so good. So what is this? B1 prime B0 plus B1 B0 prime. Do you recognize that expression? And what would that correspond to? How can I write it in an alternate logical function way? Yes, that's a Boolean expression. That's correct. Are there any other attributes of that? Do you recognize this? Is there any other way I can write that same thing using a different logical operator? Wouldn't it be just one? B1 prime B0 plus B1 B0 prime? No. If it was something like this, B1 B0 plus B1 B0 prime, that would have been a 1. In other words, x plus x prime would be a 1, but not in this case. That's an XOR, right? You must have recognized it from your test. That corresponds to an XOR operation. So I can, instead of writing this in terms of fundamental gates, I can write this as an XOR operation between B1 and B0. So let me do that. That will be B1 XOR B0. All right. What about this expression? B1 prime B0 prime plus B1 B0. What would that correspond to? Do you recognize that? That corresponds to an XNOR. Absolutely right. So let me do that then. Let me write it down as an XNOR operation. That's B1 exclusive. So I will write the XNOR operation as an inverted version of XOR, right? But because XNOR is nothing but the inverting the output of an XOR gets you the XNOR. So let me write that in that fashion in terms of the XOR operation. Again, same thing here. B1 prime B0 plus B1 B0 prime would be an XOR between B1 B0. So let me do that. And finally, we have B1 prime B0 prime plus B1 B0, which is an XNOR between B1 and B0. So let me also do that here. That would be B1 exclusive or B0. Because it's an XNOR, then I will just do that. Okay. All right. Now I see that in these expressions, I see again terms that has this part as a common factor. You see that? B1 exclusive or B0 here. I have B1 exclusive or B0 also in this expression. I have B1 exclusive nor B0 here. I have B1 exclusive nor B0 also in this expression. Right? So what I will do is I will take B1 exclusive or B0. So I can write this B0 as B1 or B with B0 exclusive or B1. Either way, it's the same thing. I take this as a common factor and combine this term that I have here with this term. So what I have here is B3 prime, B2 prime plus I'm combining this with this one which had the same factor. That will be B3, B2. Okay. And same thing here. I take this as a common factor between this expression and this expression, and I will get B0 exclusive or B1 times, what do I have? I got B1 exclusive or B0. I'm sorry, that's B1 B0 exclusive. I took that as a common factor, and then I have B3 prime B2 or B3 B2 prime from this expression. Okay. All right. Again, if I look at these expressions, this would correspond to an XNOR between B3 and B2. So let me actually replace that with the corresponding XNOR operation. So as you can see, I'm not eliminating anything. All I'm doing is I'm just expressing that expression using a different logical operator, right? So So in this case, that will become B2 exclusive NOR B3. And here I have B3 prime B2 plus B3 B2 prime. Again, I would replace that with B2 exclusive OR B3. Okay, so my P0 now becomes P0 exclusive OR B1 and B2 exclusive OR exclusive NOR B3 plus B0 exclusive NOR B1 times B2 exclusive OR B3. Okay. If I call, so we don't need this anymore, so let me take this out. If you notice this, if I call B0 exclusive OR B1, let's say I call that as X, I will call B2 exclusive OR B3 as Y. Okay. So what is my P0 then? My P0 now becomes B0 exclusive OR B1, which is X, times B2 exclusive OR B3 prime, right, prime, which is Y prime, or B0 exclusive OR B1 prime, B0 exclusive OR B1 prime, that which basically corresponds to X prime, B2 exclusive OR B3, which is Y. Right. What do I have? I have another exclusive OR operation now between X and Y, XY prime plus X prime Y, which is nothing but X exclusive OR Y. Again, replacing X and Y values, basically what I have here is X is B0 exclusive OR B3, B1, that's how I defined X, exclusive OR with B2 exclusive OR B3. So it's basically, I don't really have to have these brackets anymore. Basically what I end up is a bunch of exclusive ORs between each individual variable. Okay. A really complicated looking expression, especially when I have a K-map that looks something like that, where each individual cell, each individual one is by itself a prime implicant, could be expressed as a bunch of XOR gates, a bunch of XOR operations between the input variables. Okay. All right, so that's how my P0 is. That's how I would basically obtain my P0. And the circuit, how would the circuit look? If I want to draw that, if I want to implement that, a circuit would be essentially looking like this, right? So I have B0 exclusive OR, I have B0 exclusive OR B1, which is being exclusive ORed with B2, and the output of that is being exclusive ORed with B3. So I use another exclusive OR gate here, and I get my P0, my parity bit, the corresponding OR parity bit. Okay, and that's it. So that's how I would implement my OR parity generator. Now that I know how this looks for 4 bits, can I implement that for 7 bits, for example? And I can imagine that, I don't have to do the K-map for a 7-bit parity encoder or 8-bit parity encoder. I can imagine that my P0 would be basically, B0 exclusive, a bunch of exclusive OR operations between individual bits. So I can extend it for any number of bits, 5 exclusive OR, P6 exclusive OR, P7. But that would be for 8 bits, how my parity generator would look for an 8-bit parity. I don't have to do the K-map for 8 bits. You can imagine 8 bits, that means 2 power 8 combinations, 2 power 8 cell K-map, right? Now that will be much more complicated. But I can see that if that's what it looks like for 4 bits, I can easily extrapolate for 8 bits. Now, if I want to design an even parity, what would I do? How can I transform that into an even parity generator? What should I do for an even parity? What would the circuit look like? Take the inverse. That's it. That will be for even. That will give you my even parity, PE. Okay, so that's good. So, any questions on this before we move on to the next important topic, where so far we have designed some, discrete functions that could be useful, that can perform some operations, some meaningful operations between the inputs, on the inputs. Now, what we want to do now is to move forward with more concrete examples of how we can actually utilize or use the design principles we have learned so far in designing more concrete examples, like, for example, a calculator. How can you design a calculator that can perform operations? Or let me start by making it very simple. Okay, what's the difference between P0? P0 stands for the odd parity. PE stands for even parity generated output. Okay, that's the difference. P0, when I did the odds, this expression that we derived is for the odd, so that's why I do not have an inverter here. For even parity, all I have to do is just invert that output. I get the even parity. Okay. All right. So now we are moving forward with the design of more concrete examples like adders, for example. Adders or circuit that can perform computations. Okay, simple computations. Adding at this time, let's focus on additions and subtractions. Okay, because if you observe, if you take a close look at the more complex operations like multiplication and division, for example, these are derived from additions and subtractions. Really, there's not much different. Once you know how to design an adder or a subtractor circuit, you can extrapolate it to designing a multiplicator or a divider. Okay. All right. So let's actually start doing that. Any questions before we move forward with that design? Okay. So let's do that then. If you don't have any other questions, I hope that's clear. So now we are trying to look at the arithmetic circuits. All right. For now, let's focus on binary. That means I'm working with binary numbers. I want to design a binary adder. Okay. All right. So let's do that. I want to design a binary adder. How do we design one? Okay. Let's start with the simplest case where I want to add two binary bits together. Okay. So what I'm trying to do, again, going back to the block diagram. So here's my 1-bit binary adder. What it's doing? All it's doing is taking two binary bits together. So I have two inputs to the system. Let me call that P0 and A0. So those are my two inputs, two binary inputs. And how many outputs would I have for this binary adder, by the way? I'm trying to design this which can add two binary bits together. Okay. So inputs, I know how many inputs do I have. I have two inputs, A0 and B0. What about the outputs? How many outputs should I have for this system? So let's see. Jacob, what do you think? What's your guess on this one? One, okay. Let's do that. Let's actually see if one is good enough. Let me call that the sum, because ultimately I want the sum, right? And let's draw the truth table now. For this, I have A0, B0, and let me call it sum. And let's list out all possibilities here: 0, 0, 0, 1, 1, 0, 1, 1. What my system is doing is trying to add those two numbers together, two bits together. A0 can be 0 or 1, B0 can be 0 or 1, trying to add them together. So my sum bit would be the addition of those two bits. So 0 plus 0 is, of course, 0, so that's good. 0 plus 1 is 1, 1 plus 1 plus 0 is still 1, but 1 plus 1, what would that be? What is the binary sum? 1 plus 1. 1, 0, right? 1 plus 1 is 2. It's not 0. I'm trying to add those two bits. So 1 plus 1 is 2, and 2 in binary is expressed as 1, 0. As a 2-bit number, it will be 1, 0, right? So I need to have another output. Let me call that carry out, right? Just like when I'm adding 9 to 1, 9 plus 1 is 10, right? That means I need to have two digits to represent the sum beyond 9. Likewise, here I need to have two digits to represent, or two bits to represent the sum beyond 1, right? For binary, I need to have two bits to represent the sum beyond 1. Okay, so let me call that C out. 0 plus 0 is 0, so C out is 0. 0 plus 1 is 1, C out is 0. 1 plus 0 is 1, C out is still 0. 1 plus 1 is 2, my C out is 1, sum is 0. So I read this as my sum. 1, 0 is my sum, which is 2. So I need to have two bits for the output. Okay. And what is my sum? As a function of A0 and B0, for a simple adder, what is S as a function of A0 and B0? That's my S. That's the input combination. I can see that basically is nothing but my S is 1 when for these two combinations. That means my S, I can express S as A0 exclusive OR B0. That's nothing but the truth table for an exclusive OR gate, right? So I can directly write that expression. What about C out? What can you say about C out based on the truth table? Yeah, A naught and B naught, right? My C out is 1 where both A naught and B naught is 1. For the rest of the input combinations, in other words, if my input combination has at least 1, 0, then C out goes to 0. That's a clear cut and operation between A0 and B0. There you go. So you have designed your first adder, a single bit adder that can perform addition operations between two bits. Okay. Well, 2 bits, I can easily design it. I mean, I don't really need to design a circuit that would help me perform 2-bit addition operations, right? It's kind of obvious. Not very exciting. So let's actually do something else. I would like to design, let's say, so that's a single bit adder. That's a single bit adder. Not very exciting. I mean, it's not very exciting. At the same time, it's not very useful, not very practical. We don't need it, really. I can do it in my head easily. I don't have to really have another hardware circuit doing that for me. Okay. All right, so that's my single bit adder. Let me actually do something else. I would like to extend it to 2 bits. All right. I would like to extend it to 2 bits. That means I'm trying to add something like this: A0, B0, two numbers, two 2-bit numbers. So I call A1, A0 to B1, B0. trying to add two 2-bit numbers together and look at the sum and the of the addition process. So my sum will be S0, S1. These are the outputs. How many outputs should I have for this? If I want to design this again, in the form of a level 0 diagram, I'm applying A0, A1. That's my first number, and then B0. Let me put it this way. It should be A1, A0, B1, B0. That's a 2-bit adder. Now I'm trying to design a 2-bit adder. Now let me ask you this. How many outputs should I have for this particular adder? Yes? Johnny? What's your take on this? I know somebody wanted to talk. Eric, okay, let's see. 3, okay. So 3, okay. So I have 3, so I have 3 is as one of the answer. I have 4 as another answer. Okay, 2 sums and a carry out. Okay, so I have 2 sums. That's good. Well, let's take an example. Let's add the worst case scenario where I have 2. I'm adding 2, 3s together. Right, that's the 3. That's the largest number I can represent in 2 bits. Right, 3 to 3. So I'm adding 2 largest numbers in 2 bits together. Let's see what I get. So I have 1 plus 1 is 0, 1, or 2. 1 plus 1 is 2. So that's 0 and 1. 1 plus 1 plus 1 is 3. 1 plus 1 plus 1 is 3, which is basically 1, 1. So that's the largest sum I can get when I add two bits together. That's the largest possible sum I can get. So how many outputs then? I need to have 3 outputs. So 2 for sum, that's my sum, and that's my carry out. I'm gonna call that carry out because that's the output carry, right? That's coming out as an output carry. So let me call that carry out. So yes, 3 is the correct answer here. So let me call that C out, S1 and S0. Okay. Now 2-bit numbers, yeah, I can do it easily. I can draw the regular K-map, and I can express, and the process, right? You know exactly what these outputs are, how many outputs I have, how many inputs I have. I know exactly how to draw the K-map, how to draw the truth table between the outputs and the inputs, right? So I will basically be doing something like this. I have A1, A0 is one of the input, B1, B0. I'm not going to complete this table, but you can see what I'm trying to do here. And then I have C0, S1, S0, so 0, 0, 0, 0. I'm adding 2 numbers together, 2 zeros together. Of course, my sum is 0, 0, 0, 0, 1. So I'm adding 0 to 1. My sum is a 1. So that's basically 0, 0, 1, 0, 0, 1, 0. I'm adding 0 to 2. My sum is 2. So on. Then I have, let's say 0, 1, 1, 0. So I'm adding 1 to 2. My sum is 3, right? So that gives me 0, 1, 1. Then I add 1, 0. Okay. And you can, and then finally I have, and so on, 1, 1, 1, 1. I'm adding 3 to 3. My sum is 6. and I will get, what do I get? I have 1, 1, 0. Right? 2, that's 3 plus 3 is 6, and that's 6. Now I have the truth table. I can compute what is C0 as a function of A1, A0, B1, B0. Compute CS1 as a function of A1, A0, B1, B0. Compute S0, and so on. Again, the same procedure that we have illustrated in the last few classes. So that's more of a mechanical approach now. Okay. But again, if you look at it, it's not very exciting. I'm two bits added together. I can do it in my head. I don't need a calculator for that. Right? You would agree with that, right? Because the largest sum I can get is basically 6. And I can easily do that in my head. I don't need a calculator for that. What about 3 bits? When I do 3 bits, how many inputs do I have and how many outputs would I have? I'm trying to add 3 bits together. That means here I have an additional bit for A. Let me call that A2, A1, A0. Then I have B2, B1, B0. And you can guess that this will be S2, S1, S0. I have 4 outputs, manageable, but I have 6 inputs. Implies if I want to do the K-map approach, I'd be needing 2 power 6 cell K-map or 64 cell K-map. And the complexity increases every time I add an additional bit. If I want to do 4 bits, right? If I want to add 2 4-bit numbers together, how many inputs would I have? I would have 8 inputs, right? That means I would have 2 power 8 cell K-map. I would be needing 2 power 8 cell K-map, and it's just after this stage, it just doesn't get practical. It just cannot use the K-map approach and try to design your adder using the fundamental gates this way. Okay, it's like building a large structure instead of trying to, let's say the best analogy would be trying to build a large structure, putting together the sand particles together. And that's really not the best approach, right? You don't want to do that approach. You can build it in practice, obviously, yeah. You can put the sand particles together, bind them, and then somehow construct a large skyscraper or large building together, which is, in theory, it's practical. It's possible, but it's not very practical approach. So we have to think about some other approaches. Okay, and that brings us down to another important concept of modular design. Just like how houses nowadays are constructed, right? These are all modular in design, right? So you have these pre-built structures that you get and then assemble together to form the whole structure. That's a much more efficient way of designing things instead of trying to build everything from the scratch. That may not be the most feasible approach, most practical approach. Okay. All right. So what does that mean? So let's actually look at the modular approach. And this approach is not just relevant to this class. This modular approach is the way to go. When you're trying to design any engineering system, the modular approach is the way you'll be doing things. Where you design these modules, individual modules that can perform simple operations, and then you put them together to perform a more complex operation. Okay, so you're not working at the individual gate level, you're working at the modular level. All right, so modular approach. You would still be using K-map approaches and so on that you have learned, but only to design the simplest of the module. And then from that stage, we'll be working on the modular, on the actual pre-built modules. All right. Now, let's examine let's actually examine the addition operation in more detail. All right. So let me just generalize this now. I want to add two n-bit numbers together. This n can be a large value. N can be 32-bit. Right now we are working with 64-bit computers. That means most likely we have a 64-bit adder within our computers, right? So n can be a large number. I'm not too worried about n now. I want to generalize this. So I'm trying to add two n-bit numbers. Let me call them a n minus 1, a n minus 2, a n minus 3. Let me call this some intermediate bit position ai, so on, a2, a1, a0. So again 0 to n minus 1, that's basically n bits, n digits, or n bits. I'm trying to add that to another number b, to another binary number bn minus 1, bn minus 2, bn minus 3, some intermediate bit position bi at the same position, b2, b1, and b0. Okay, I'm trying to add these two numbers together. The reason why I want to do this exercise is to see what kind of modules would I want to design in this case. Okay, so this is how I'm going to do this. So how do we do this addition operation? I start with the rightmost bit, right? I add these two bits together, a0 plus b0. I get some sum, right? Let me call that s0. And I may get a carry out. Let me put it this way. I get a sum s0 and I get a carry out that could be a 0 or a 1, right? When both a0 and b0 are 1s, then basically I get a carry out of 1. When a0, when one of the number is 0, I get a carry out of 0. So let me just say that, say the carry out as C0 in this case. Okay. This carry out, I'm going to add that carry out to the next bit position. And that's how you do the addition operation, right? So let's say you have two, okay, let's do binary, 1, 1, and 1, 1. I start with the rightmost bit, I add them together. I have 1 plus 1 is 1, 0. So 0 gets left over here, and then carry over the 1 to the next bit position. And then when I'm adding in the next bit position, I add the two individual bits together along with the carry out. That's the typical way we do addition operation, right? And that's 1 plus 1 plus 1 is 3, 1, 1. So now in this bit position, I'll be adding A1, B1 along with C0 to give me some S1, let's say, and a carry out. Let me call that C1 that goes here. Same thing repeats. In this bit position, I'm adding A2 and B2 along with C1 to get my S2 and some carry out C2 and so on, and that gets propagated, and basically you're propagating it through the entire bit position. So in this intermediate bit position, what do I have? I get some get carry out from the previous bit position. Let me call that Ci minus 1, right? The carry out from the previous bit position is Ci minus 1. I'm adding that along with these bit positions Ai and Bi to get my Si, and an output carry, let me call that Ci, which gets added on with the next bit position, right? Now, if you notice clearly, at every individual bit position, I'm doing the exact same operation. Of course, my inputs may be different, but the operation itself is identical, right? I'm adding those two bits along with the previous carry, producing me an output and the output carry, output sum and an output carry. And this exact same operation is repeated at every bit position, right? So that's good news. What that means is, what if I can actually make this a module, a simple circuit that can perform just this operation, because every bit position performs exactly the same operation. What it entails is I would basically construct that module and replicate that, copy and paste it. and then I would basically connect them to these modules together in whatever way possible to form this entire adder. So that's the design approach we will take now. Okay, I hope that makes sense. I hope you are with me until this point. All right, so let's do that. So I'm trying to design this module here. All right, so let me put that down, my level 0 diagram. Let me identify, let me call that a full adder, a 1-bit full adder, okay, a single bit full adder, because ultimately it's basically adding 2 individual bits. It's called a full adder because it's also considering my previous carry. That's why we call it the full adder. On the same lines, the adder that we have come up with, the single bit adder that we discussed just a few minutes back, that would be considered as a half adder. Half adder because this is something where we designed 2 bits being added in A0 and B0 without considering the previous bit, without considering the previous carry, producing you the sum S and C out. So that would be the half adder circuit. So you can note down in the previous example where we did the single bit adder, that would be a half adder. Now what we are trying to design is a 1-bit full adder circuit. What are the inputs to this? How many inputs do I have for this 1-bit full adder circuit? 4. Okay, what are the inputs? Okay, I have many 3s. I have 1 4. So my inputs are, I'm adding the individual bits together, which are AI and BI. So I have 2 of them here. I'm adding that along with the previous carry, which I call it Ci minus 1, or maybe here it's a little confusing. Let me just do that. I have 3 inputs, Ci minus 1. Okay, and how many outputs would I have? When I'm adding 2 individual bits along with the previous carry, how many outputs would I be expecting to get? The answer is right there. I'm adding these together to get what and what? 2 outputs, right? To get the sum and the carry out, right? Yes, 3 inputs and 2 outs. That's exactly right. So let me call that. So this is my Ci and Si. So I'm trying to design a module that can perform this operation. And when we have to design this. Now let's set out to design this. Okay. So with this information, things are much more clear now, right? So you see the importance of this approach, importance of coming up with this level 0 diagram, right? Now I know exactly what my inputs are. I know exactly how many outputs we have. I know the relationship between those because these outputs are produced when I'm adding these bits together. So I know exactly the relationship between those outputs and the inputs. Now it's time to put this information down in the form of a truth table. Okay, let's do that. So now, from now on, it's more or less, set, right? The difficult part, the thinking part of the problem is done. So now we just have to do the truth table, which relates my inputs, which are Ci minus 1 and AI BI. So those are my inputs. And 2 outputs, which are Ci and Si. Okay. So I have 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1 1 1 0 1 1 1. So I have 8 different combinations between the inputs. How do I get the outputs? I simply add each individual bit together. So 0 plus 0 plus 0, 0. So my C is 0, Ci is 0, Si is 0. 0 plus 0 plus 1, the sum is 1. 0 plus 1 plus 0, the sum is still 1. 0 plus 1 plus 1 is 3. 0 plus 1 plus 1 is 2. That's 1, 0. 1 plus 0 plus 0 is 1 again. That's 0, 1. 1 plus 0 plus 1 is 2. 1 plus 1 plus 0 is 2. 1 plus 1 plus 1 is 3. You get that. Okay. Now, if you think about this SI and relate it to the problem that we have just done, the what is that? What is the problem that we have just done? The parity bit, right? You can see if the number of zeros or if the number of ones is odd, my SI is a 1. I mean, do you observe that? It almost functions, my SI almost functions as an odd parity bit generator. I would not say almost, it actually functions as an odd parity bit generator. Also, although we did not intend it to be like that, it turns out that my SI actually is an odd parity bit generator. If you notice the input bits to my system, if the number of ones are odd or is odd, my SI is a 1. It's a 1 here. That's even number of ones, my SI is 0. Odd number of ones, SI is 1. Even 0. Even 0. Odd number of ones, my SI is a 1. What can you say about SI without really going through the K-map approach, which you can do it to verify it, which is fine. But without even doing that, what can you say about SI? How can you write SI as a function of Ci minus 1, Ai, and Bi? XOR each one, absolutely right. That's exactly what we got, right, for the odd parity generator. In this case, SI is actually functioning as an odd parity generator. So, and if you recall from just a few minutes back, I can extrapolate the same result for 8 bits. We have done it for 4 bits. The way to extrapolate that to 8 bits is basically XOR between the inputs. Just add more inputs and then XOR between the inputs, you get the 8-bit odd parity generator. In this case, it's just a 3-bit parity odd parity generator. So I can simply write SI as Ci minus 1 XORed with Ai XORed with Bi. I don't have to do all the K-map approach here. I can simply write it down that way. And I would like to like you guys to actually do it, work it out using the K-map and verifying that that's indeed the case. You will get the same thing, but I would like you to go through this process as a practice. Okay. For Ci, I may have to just do the K-map. I'll do the K-map. So at least I have eliminated one step in my process. I can just something that I've already observed, I'm able to directly write down what my SI is as a function of inputs. Okay, let's do CI. So that's an 8 input K-map. That's between Ci minus 1, Ai, Bi, that's 0, 0, 0, 1, 1, 1, 1, 0, that's 0 and 1. And I have 0, 0, 0, 0, 0, 0, 1, then 0, 1, 1, 1. That's 0, 1, 1, 1. Okay. And now I have to combine the terms. It's actually pretty simple. That's one combination, that's another combination, that's another combination. And what do I get? So my CI, again that's for CI. So my CI may be expressed in terms of AI, BI, and CI minus 1 as AI, BI from this combination. And here I have CI minus 1 times BI plus CI minus 1 times AI. Or I can write this as AI, BI plus, I can take the CI minus 1 as a common factor. I'm not eliminating anything. It's not going to give me any further simplification because I have chosen the right prime implicants. I don't expect it to be simplifying any further, but I'm just writing it in this format. AI exclusive or BI. Okay. Now, if you recall, in the last class, I mentioned something about systems that have multiple inputs, right? When you're trying to design a system with multiple inputs, with the same set of multiple outputs, with the same set of inputs, I'd like to make sure that I would like to see if I can reuse some of the product terms from other implementation, from other outputs in implementing another output. Okay, that's maybe that's a mouthful. What I'm trying to say is, here what I have is a CI minus 1 AI BI obtaining CI and SI. I have two outputs. Okay, I can implement them independently, which is fine, which is still work. But can I be able to use some of the product terms from SI, because they are being implemented, in implementing CI? That way, I don't have to. I can reduce the redundancy in my circuit. So that's my idea. Okay. So let's see. Can I do this? For SI, basically it's CI minus 1 exclusive or AI exclusive or BI. So let me see if I can combine the ones in a different way, even though that may not be giving you the most optimal combinations. If I can combine them in this way and see what you get, something like that. So that to reduce the redundancy in my circuit, so that now I get my CI as, again, AI BI. I still have to account for all the ones. Then what I have that CI minus 1 and then I have AI prime BI plus, actually let me combine it this way. As you can see, this is obviously not the best way to move forward with K-map. If I had a single function, I would definitely not be combining it in this way, as CI minus 1, because that will not give me the most simplified function. I get AI BI prime, or my CI will be written as AI BI, taking CI minus 1 as a common factor. I have AI prime BI, AI BI prime. This is definitely not the prime implicant, but by combining this way, I can write this as AI exclusive or BI. Why am I doing that? Because I notice that my SI already has AI exclusive or BI computed. I might as well use that in the implementation of my CI. So I can reduce an additional need for an additional OR gate between AI and BI, which we got for the initial for our initial trial. So that's it. So my function for the full adder now looks like that's a single bit full adder. I can write that down. I can actually draw that down now. Okay, I have Ci minus 1 applied, AI, BI, my Ci, and then my Si would be a bunch of exclusive OR gates. So that's AI exclusive OR BI, exclusive OR with Ci minus 1. That gives me my Si. All right, and then I have Ci as AI BI. So that's my AI. And BI. Plus, plus Ci minus 1. That's my Ci minus 1. Times, so that's the exclusive OR between AI BI. Okay, where is this? AI BI plus Ci minus 1 times okay. Let me make sure that's correct. So that's AI exclusive OR BI times Ci minus 1 plus AI BI. That's correct. So that's my Ci and that's my Si. Okay. All right. So we'll stop here. And so we have built one single module. Of course, we have to now implement the whole entire n-bit adder module using copies of the single bit full adder modules. Okay, and that's something that we will talk about in the next class. So we'll stop here. Any questions before we move on, or before we conclude completely for the class?